irreversible. That means the energy involved at the initiation stage of the reaction must be enough to Good morning, students. Unique Izuchukwu, my name, DeGuru himself. We are discussing redox reaction, Chem 101.1. Much has been said, and you told me that you followed me 100% yesterday. Today, we are diving into another special aspect of the show. How do we develop? How do we balance half reactions? How do we develop? How do we balance half reactions? Somebody may wonder, why half coming before reaction? Yes, a redox reaction is one reaction. But that reaction is made up of two things. We agreed yesterday, two processes. Reduction process, oxidation process. Both processes come together in one reaction to give us what we call redox. One reaction. That means I can divide that one reaction into two half reactions. Reduction half, oxidation half. When the two half reactions are brought together, it gives us what we call redox reaction. Now, in your exam, they might give you a compound and ask you to develop reduction half reaction for it or oxidation half reaction for it. Don't forget, oxidizing agents are reduced in a chemical reaction or redox reaction. The oxidizing agent is reduced while the reducing agent is oxidized. That also means that in a redox reaction, there are two agents you must know involved. There is a reducing agent that reduces the oxidizing agent, and there is oxidizing agent that oxidizes the reducing agent. So every redox reaction must also have a reducing agent and what somebody oxidizing agent. If that oxidizing agent or reducing agent exists as a compound and you're asked to develop and balance the half reaction involving that agent, that is the principal focus for today's discussion. Follow me as we take a typical example of the man of the moment. KMNO4. Questions are always asked based on this man. This is a known higher oxidizing agent. In a redox reaction, it is reduced by a process we call reduction half. By the way, the KMNO4, as you see here, is made up of two parts on dissociation. If I dissociate this, I should have potassium ion plus tetraoxomanganese 7 radical. Every compound is made up of two components. Metallic ion component, non-metallic ion component. The negative and the positive. Please, whenever you're dissociating, also ensure that the system is balanced mass-wise and what? Charge-wise. +1 -1 will give me 0. Of course, you can see that potassium tetraoxomanganese 7 here is a neutral compound. So it's balanced mass-wise and charge-wise. If the man I want to dissociate is Cr2O7 this way, potassium heptaoxo dichromate 6. If I want to dissociate this man, see what I'm going to do. Potassium ion. Of course, you know that the valency of potassium is +1. It's number 19, 2881. It has one electron on its outermost shell. So during chemical reaction, it loses one electron to form a univalent ion. So the valency of potassium is +1. That is why I have written +1 on it. Plus, you have Cr2O7. Now, the charge you're going to put here depends on the overall charge of this potassium. First, balance mass-wise. We have 2 atoms of potassium here, but there is only one atom represented here. So what am I going to do? I need to multiply this person by 2. When I do that, it means that the overall oxidation state of potassium here has become +2. Remember, you must multiply the power by the coefficient. +1 times 2 is +2. So to make sure that the whole of this place becomes 0, which is the 0 I have this side, it means that I must bring in 2 minus here. So that -2 + 2 boils down to what? 0. Please, what I have taught you now is how to dissociate, how to split a compound into its component ions. KMNO4, potassium tetraoxomanganese 7, is neutral. It has 1 atom of potassium inside it. That's why I represented just an atom of the potassium ion here. That is different from what is happening in the case of potassium heptaoxodichromate 6. Potassium here has 2 atoms. So while producing the ion, I must also make sure that this system is balanced mass-wise. No wonder I have introduced 2 here, which has given me 2 atoms of potassium here. But these 2 I introduced here is symbolic. It has a significance. It has made the overall oxidation state of potassium here to become +2. The implication is that if this place is +2, what I must bring in here must be -2. So that -2 + 2 will boil down to 0 to make sure that the 2 sides of this equation are balanced, not just mass-wise, but what, somebody? Charge-wise. So having said that, the next thing we'll be talking about is, out of the 2 components that make up this compound, metallic component that is positive and the non-metallic component that is negative, as you can see from our dissociation, the question becomes, which of them is the active component in this compound? Please let me remind you, class, that every compound is made up of what we call 2 components in terms of whether it's oxidizing or reducing. Out of the 2 components, one is going to be a spectator, a monitor, an ordinary observer in that chemical reaction. It doesn't partake in the reducing or oxidizing process. The major component that does the oxidation, the major component that does the reduction, is what we refer to as active component. So it will interest you to know that there is a way you can identify a spectator ion, identify active component. Why are you identifying them? Because in a redox reaction, we actually do not represent the spectator ion when we are representing ionic redox equation. So the onus is on us to identify the spectator ion, the one that is not doing any job in that compound, to eliminate it and take up only the active component. Simple rule. Watch me. Negative component of oxidizing agent is active. Positive component of a reducing agent is active. Now, take this to the bank. KMNO4 has 2 parts, the positive and the negative. I have said negative component of oxidizing agent is the active component. That means that the positive part is the spectator. Positive component of a reducing agent is active. That means that if the agent is a reducing agent, the negative part has nothing to do with the oxidation or reducing process. So, bring it down. This man here is an oxidizing agent. The positive component has nothing to do with the oxidizing property of this person. So I will identify this person as a spectator ion, whereas this person will be considered as active component. And that is the man I'll be working on in my today's developing and balancing. Now, having identified the spectator ion and eliminated it, let's look at the active ingredient. the man that does the oxidation in KMNO4. Class, follow me. All right, we have MnO4 minus. Again, this is tetraoxomanganese 7 radical. You may wonder, why did I say manganese 7? You can work out that on your own. Find out the oxidation state of manganese inside this radical. How do we do that? This one is O level, MnO4 minus. If I'm looking for oxidation state of manganese, I will take it up, plus, this is oxygen. What is the valency of oxygen? You know now, minus 2. Configuration of oxygen is 2,6. 2,6. So oxygen has to accept 2 electrons to complete the outermost shell. So because he's getting -2, he's getting 2 electrons to complete the outermost shell. That's why the valency of oxygen is -2. So I'm going to write -2. How many atoms of oxygen do you have here? There are 4 of them. Multiply by 4 equates to the overall oxidation state, the charge on it, which is -1. If there's no charge, equates to 0. So manganese -8 is equal to -1. So manganese will be equal to -1 plus 8. This man crossing the sign of equality. So manganese will be equal to +7. Class, you can see clearly that the oxidation state of manganese here is +7. So, if manganese is in MnO4 minus, I'm taking my time today. This is MnO4 minus. And the product side, because the oxidation state of manganese here is +7, and the product side, it will go to the next lower oxidation state, which is +2. Manganese is a transition metal. Manganese is a transition metal. We know the general properties of metals. They are malleable. That means you can break them into sheets. They are ductile. You can draw them into wires. They are sonorous. If you hit them, they can produce sound. They possess luster property. That means if you polish them, they will shine. They are, they are ionized by loss of electrons. That's why they are reducing agents, metals. Most of them remove hydrogen from acids. They are good conductors of heat and electricity. They have mobile electrons. These are basic properties of metals. But in addition, transition metals have 4 properties that are peculiar to them. They have the ability to function as catalysts. They have the ability to form colored ions. They have the ability to form complex ions. And they exhibit what we call variable oxidation state. That's one that brought me to the gist. Transition metals exhibit variable oxidation state. Who are transition metals? Those of them between 21 and 30. Scandium, titanium, vanadium. You know them. Sicilian T vanadium cream. The cream there is chromium. Main fed cobalt. That's manganese, iron, cobalt. Nigeria cut Zambia. Nickel, copper, and zinc. 10 of them constitute transition metals. They exhibit variable oxidation states. That is why somebody can talk about copper 1, copper 2. That's why somebody can talk about zinc 1, zinc 2. That's why somebody can talk about iron 2, iron 3. You cannot talk about sodium 1, sodium 2, because sodium is not a transition metal. It does not exhibit variable oxidation states. Transition metals do. For manganese, there are 2 oxidation states, +2 and +7. So, having identified that the oxidation state of manganese here is +7, at the product side, it will go to the next oxidation state, which is +2. By the way, why is it going to the lower oxidation state? Remember that this is the active component of this oxidizing agent. So it has to be reduced from +7 towards somebody, +2. Alright, having said that, I will start my balancing. 1 atom of manganese, 1 atom of manganese, I don't have issue with that. How many atoms of oxygen here? 4. So, the rule says, balance oxygen with water. Balance oxygen atoms with water. Of course, after that, we'll be discussing what we call balancing in acidic medium and balancing in basic medium. Balance oxygen atoms with water. Balance hydrogen ions or hydrogen atoms with hydrogen ions if it's in acidic medium. And that is what I'll be doing here. Balance charges with electrons. We balance charges with electrons. Okay. We balance oxygen atoms with water. We balance hydrogen atoms with hydrogen ions in acidic medium. And we balance charges with electrons. Wake up, wake up, wake up. Follow me, follow me, follow me. We're going to somewhere. All right. We have 4 atoms of oxygen here. So I need to bring in 4 molecules of water to balance it. Because we balance oxygen with water molecules. This is water. If you bring in 4 atoms of oxygen or 4 molecules of water, you have brought in 4 atoms of oxygen. But something has also happened. You know, water contains hydrogen and oxygen. If I balance oxygen by bringing in water, I have also created, the rule says, balance hydrogen atoms with hydrogen ions. So I will come to this place and put 8 hydrogen ions. What is the next? We check the charges. Because the system must be balanced mass-wise and charge-wise. Follow me. The overall charge here is -1. The overall charge here is +8. So I have -1 plus 8, which will give you +7. That is the overall charge this side. Let's come to this side. The charge I have here is +2. And of course, in water, we have 0. +2 plus 0 remains +2. So the system is not balanced charge-wise. +7 plus 2. It's either I increase +2 to +7, or I reduce this +7 to +2, so that the system becomes balanced. How do we balance charges? With electrons. What am I going to do to reduce +7 to +2? By subtracting 5. Subtracting 5 means bringing in 5 electrons. You know that the electrons are coming with negative charges. So if you bring in 5 electrons, you have brought in -5. -1 times 5 is -5. So -5 plus 7 gives you +2. You have that side, making this system to become 100% balanced. By the way, if I want to work on this side, balancing charge-wise, I'm not going to bring in 5 electrons. I would rather subtract 5 electrons. Why am I doing that? -5 times -1 gives you +5. So +5 plus 2 will give you the +7 you have this side. All right, ladies and gentlemen, this is how we can develop balanced half reaction for KMNO4 as example number 1. As I come your way, just in the next lesson, we are going into other examples, how to develop balanced half reactions. And of course, we are going to be diving into how to balance overall redox equations in the process. Thank you so much for having an encounter once again with the Guru himself. Feel free to ask any question that bothers you. Subscribe to the Guru's Mathematics Science app. You'll be very happy with yourself. Thank you so much, and God bless you.